Hi all, welcome to Learn Code Repeat. Today we will be looking at day 6 of the October LeetCode challenge. The name of the problem is insert into a binary search tree. Let's look into the problem. So the problem says you are given root node of a binary search tree and a value to insert into the tree. Return the root node of the binary search tree after the insertion. It is guaranteed that the new value does not exist in the original BST. Notice that there may exist multiple valid ways for the insertion. As long as the tree remains a BST after insertion, you can return any of them. So what is a binary search tree, right? So the property of binary search tree is the child node to the left should always be less than the parent node, and the child node to the right can be greater than or equal to the parent node, right? That is the binary search tree. So while we insert the new node into the binary search tree, we have to make sure that the property is valid. That means, let's say here I am inserting 5, right? What will I make sure is if 5 is greater than 4, my root node. If it is greater than or equal to my root node, I need to move to the right and again do the same check. Else I need to move to the left. So here, since 5 is greater than or equal to 4, in this case it is only greater than 4, I will move to the right and check with the child node which is on the right of the root. So here the next node is 7. So 5 is less than 7, so I will move to the left of 7. But in this case, since the left of 7 is empty, 7 is the leaf node, so we will add 5 to the left of 7. So whatever position where the node is empty or the node is leaf node and we can insert this node there, we should insert it in that position. Okay. So let's take another example, right? Let's say instead of 5, right, after this tree is formed, if I need to, let's say I need to insert 0, right? So again I will do the same comparison, 0, so I need to insert 0, 0 is less than 4, so I will go to the left of the tree. I will again compare it with the next node, 0 is less than 2, so I will go to the again left of the tree. Again 0 is less than 1, but 1 is the leaf node, so there is no child node in 1, so we can add 0 to the left of 1, so 0 will be added here, right? Now let's say if I take 9 as the example, right? Here 9 is greater than 4, so I will go to the right of the tree. So it will compare with now 7, 9 is again greater than 7, but there is no child node to the right of 7. Okay, so I can directly add 9 here to the right of 7. Okay, so this is how we can traverse through the binary search tree and add the node in the binary search tree. Now what we did here, we will try to code the same thing in the algorithm, right? So what we are trying to do here is we are comparing with the current node's value, and based on that we are trying to decide whether we need to go left or whether we need to go right. So the condition is if the current value is less than my node value, then go left, else we have to go right. Okay, so let's code that condition here, right? So here in the code, right, I have written this two condition, right? If val is less than root dot val, then I need to go to left, else I need to go to right, right? Now if you observe, right, once we identify that I need to move to left, right, and I go to left, what are we doing after that? Again we are doing the same check. So if you see, that is a recursive pattern, right? So I can recursively call this same method here and pass my root dot left value and the value that we need to compare with, and similarly I can do the same thing for my right node, right? Now when I go through the tree in a recursive fashion, right, when should I break, when should I stop the recursion? Now if you observe here, right, we were stopping the recursion and adding the node when we find that there is no more child nodes, right? So in terms of code, if we go in a recursion and if we find that the current node is a null node, we can very well add the current value as a new node in that place, right? So how can we do that in code? So here, right, we can break this and say that if my root equal to null, then I can very well add this value as a new tree node, right? Now if I am adding this, right, I need to add it to that particular node value, right? So when I say that particular node value, so here I am adding 9, I need to add 9 to this particular 7, right? This is the parent node. So what I can do here is instead of not returning anything, I can return this whatever I am adding as a node value, and here since I am adding it to the left, so I can say that root dot left will now become this value. Okay. Similarly, for root dot right, I can say that root dot right is whatever this recursion is returning me. Okay. So what will happen here is in this case, right, if the value is 9, so 4 will call the recursive for its right child 7, and it will ask the recursive function to return me the node. Okay. 7 will call the recursive function for its right child. Now there is no right child for 7, so in that case 9 will be created as a tree node and it will give that back to 7. So what will happen here is when we are at this node, it will say root dot right equal to my this new tree node that is created, and then that will be again, so this root which is 7 node, that will be again assigned to the right of 4. So 4 will get the updated node which is 7, and 7 will get the new node which is 9. So that is what we are trying to do here, okay, when we are returning back the node. So this is the simple algorithm here with recursion. So let us submit this, and at the end we are returning the root, right. So that is what they want to return the root. So let us run this code and check whether it passes the test case. So here we are getting null null. Okay, so let us see. Okay, here it should be right. Let us run it again. It's working fine. Let's submit it, and the code is accepted. So the runtime of this algorithm will be, since we have to go through the height of the tree, right here, right, we need to find out which is the node where we can insert this value, right. So we are not going through each and every element, right, we are checking that condition left and right and going through that, right. So the complexity will be to go over this path, right, what we have, right. So the complexity here will be O of h, where h is the height of the tree. So my time complexity is time equal to O of h, where h is the height of the binary tree. So that's it for this video. Hope you like the solution. Please hit the like button and do subscribe to the channel. Thank you.